Come, please.
So good afternoon, everyone. My name is Barbara, and I'm going to be the reporter for the Senate Brazil with the problem magnetic coil. So first, I'd like to read the problem. Place a coin vertically on the magnet. Incline the coin relative to the magnet, and then release it. The coin may fall down onto the magnet or revert to its vertical position. Study and explain the coin's motion. So first we made some introduction with a threshold angle for the coin to fall down onto the magnet or to revert to its vertical position. The rotational motion, and then we analyze the oscillations. That is one of the objectives of the problem. Then we conduct some experiments, and which will lead us to a conclusion, making an analysis and a comparison with our theoretical model. So first I'd like to talk a bit about the magnetization of the coin. So magnetization is the main parameter for the effect to happen. We do know this. However, it is too difficult to quantify the magnetization for the shape of the coin and particular for ferromagnetic materials in general. Then we made an approximation to equivalent magnetic charts to make some sort of average to make our mathematical model. And then we are going to compare to our experimental data. So we consider this magnetic charge with some sort of momentum in an analogy with an electrical field, but actually it's just some sort of average to the magnetization. So we have two conditions for the stable equilibrium and one condition for the unstable equilibrium of the coin, in which the threshold angle for the coin to fall or revert to its vertical position is defined. Then we have the configuration of the system in the unstable equilibrium. So we have this first area angle as I maximize to make sure everybody's going to see this. And then the other triangle. So we have the R1 that is the diameter of the coin and R2 that is the thickness of the coin. Then we use our model for the magnetic chart, which I do know it's not the real phenomenon behind it, but it's just an approximation. And it's inverted proportional to the distance squared. So we have this distance in function of the thickness and the sine of θ1 and θ2. And both angles are complementary, so the sine of one is the cosine of other. Also, we know that the torques must be equal in the diameter and in the thickness of the coin for the unstable equilibrium. And applying our model, as we showed before, we have a mathematical model for the threshold angle in function of the dimensions of the coin. So we have that if the tangent cubed of this angle is lower than this radio, the coin falls over the magnet. If it is equal, we have the unstable equilibrium, and if it is higher, we have the coin coming back to the original position. And the magnetic properties, as we see, is not that important for the threshold angle itself, but as we're going to see, it is important for the motion, the oscillations, and whatever. And the way we neglected this for this mathematical model, but I'm going to show you my experimental data why we did this and why this can be done. So we wanted to know about the rotational motion, of course, and then we displaced the rotational axis from the center of the coin by a distance R line. And then we used the theorem of parallel axis to get the moment of inertia at this point. We applied in the torque is equal to the moment of inertia times the angular acceleration. And we got the angular acceleration in function of known parameters that we can get behavior with. So it is really dependent on the position of the coin, so it's time dependent on the oscillations. And it is also dependent on the magnetic constant C. And this magnetic constant shows that the motion is dependent on the magnetic properties of the coin. Then integrating in function of θ1 as the angular velocity is the integration of the angular acceleration with time. We have the angular velocity. And so we get the behavior of the angular velocity in function of θ1. And we see by the end of the graph that the angular velocity is approximately constant, so it can be approached to an angular velocity that is constant. So the coin is inclined in relation to the magnet in an angle θ1. It comes to the original position, and then it starts to oscillate due to some restoring forces that we acknowledge to the magnetic force itself. So the angular velocity is approaching to constant, the amplitude clearly decreases with time, and the amplitude is really low as we see. So we do first thing that may resemble an energetic harmonic oscillation, which is a type of minus BD, and then we have the equation of motion, the omega 0, the gamma that is a coefficient for damping, and omega 0 is the natural frequency for the rotational motion, and we have an angular velocity that is constant. And solving the equation of motion, we have the graphic behavior of this function. However, we do know that the magnetic force do not vary linearly with the distance. So this may resemble an energetic harmonic oscillation, but the period we need the period to vary in our graphics, in our experimental data. And what's the source of this dissipative force? We do think that is due to eddy currents, because there is a variation of the magnetic flux, which inducts electrical current, and there is a dissipative force generated during the oscillation of the coin. So we have the oscillation of an amplitude of about 5 degrees, and we have two extreme cases for a coin that's placed on the magnet. One in which the coin is on the poles, and one in which the coin is on the sides of the magnet. And we have the different values for the variation of the magnetic flux. In the first case, that is the case of our experiment, there is the maximum case for a certain magnet for the variation of the magnetic flux, and so the eddy currents would have the greatest effect in a certain magnet. So we have our material. I'm going to talk about that when I talk about my setup. And we conducted 4 experiments to agree or disagree with our experimental data with our theoretical model. First, we neglected the weight, and why could we have done this? We measured the total force acting on the coin with a dynamometer to take the average of this force, and this total force is actually the weight and the magnetic force summed. And the weight represents less than 1% of the magnetic force, so we do think we can neglect it. Then we used 8 different coins. We inclined it then 1 by 1 degree, and repeated this procedure 10 times for each coin and took the average. So we have our experimental points, and within our uncertainties, we see that our mathematical model, although considering the magnetic charge by our experimental data, we see that it fits within our uncertainty or theoretical model or mathematical model. So then we tried for 2 different magnets, because I told you in my mathematical model that the threshold angle was dependent in the dimensions of the coin. I varied the magnets and we mapped the magnetic field, so we see this is different. And then we have the average, which within our standard deviation for both, we see that the angle is the same, even varying the magnet. Then we made a video with a high-speed camera of 4,000 frames per second, and we could get the angular displacement of the coin with quite a good precision to evaluate the oscillations of it. So we made this for 2 different coins of the same thickness, but with different diameters, so the areas of them were different. The blue one is the one with the greatest area, and we see that it has the highest damping. So this is an evidence of eddy currents. Also, it resembles an underdamped harmonic oscillation, but the period clearly varies, and that's what we were expecting, because the magnetic force doesn't vary linearly with the distance. So the coin with the largest area had the greatest damping, and it's an evidence of the eddy currents dissipation by the eddy currents. So, in my conclusion, I'd like to say that the magnetic properties are important for the motion of the coin itself. And it is the initial condition for the movement to happen, for the effect to happen. So the magnetic properties are actually important for this magnetization. The threshold angle is dependent only on the coin dimensions by our mathematical model, which our experimental data is an evidence that that approximation actually works. The forward or reverting motion is due to the torques on the thickness of the coin and in the diameter of the coin in both points. So also the oscillations resembles another harmonic oscillation, as we have the amplitude decreasing with time and some oscillations, semi-function. But the period varies, which we were expecting because the force doesn't vary linearly with the distance, which we showed back our fourth experiment. And there are, in the same experiments, we have some evidence of the dissipation by interference, which we do think is a source of this dissipative force. So here it is my references if you want to check out my research, and thank you for your attention.
Thank you. Now please questions first. Lapona.
After everyone, you had the jurors, the presenter, and the reviewer. I'd like to ask you some questions. First of all, is there a specific angle in which the coin must be inclined before it falls down the
Yeah, it is actually the threshold angle I defined in my mathematical model.
Okay, so is there a specific value for it?
Yeah, and we show in our mathematical model in here, and also in two of our experiments.
No, I'm saying that could you find the angle in which it has to be inclined?
Yeah, this is the angle, the theta 1.
No, like in degrees, like the value.
Yeah, sure. Dependent on the coin's dimensions, we have different angles. And here you can see my theoretical model, and each one of these points are this defined angle for the inclination of the coin to fall or to revert to converted position.
Okay, according to the experiment, you showed that there was an initial push in the coin. So is there, how did you calculate that initial push which you gave the coin?
Actually, we just wanted to see the behavior of the motion, so we didn't control that initial push. But we took the video after a moment like some centesimals of seconds to get the oscillation. It's dependent on the magnetic force, but not on the push that we did first, because we just considered the first centesimals of these oscillations.
Okay. Can you explain the equation?
Yeah, first I'd like to know what's the equation, and I'd like the cable to connect the projector.
No.
That's the only one working.
No.
That's
it.
This one you used.
So what equation do you want to define?
On page 3.
What?
Page 3.
Page 3. Yeah, that's a page 3. There's no equation on there.
I'm going to say page 4.
Uh,
That's this one.
This is actually an analogy with electrical field, which we made to use as an average for the force, the magnetic force, and the momentum of the magnetic force in function of this so-called the magnetic charge approximation we've made.
Okay, and how relevant are the magnetic properties of the coin?
Of course, the ferromagnetic properties of the coin is the initial condition for the effect to happen, and the magnetization of this coin is actually really relevant for the oscillations and for the movement itself in all the during the motion. You talked also.
Sorry.
Okay.
How relevant are the magnetic properties of the coin. Is it possible under certain conditions for the coin to flip upside down?
Like how do you flip upside down?
Instead of just falling down, it will fall down but then stand up again at the same time.
It's like it comes to original position.
Yes.
Yes, of course it can, and this is the case of the. This is actually the case of the oscillations that we showed by our video of the high-speed camera, as I can show you here before. We've inclined this in an angle that is higher than that threshold angle, and that's why the coin reverses to the vertical position, and then it starts to oscillate, and this video can show that.
Okay. How did you calculate the magnetic force?
Huh?
How did you calculate the magnetic force?
Actually, we did not calculate the magnetic force because it was really difficult for ferromagnetic materials to calculate the magnetization and so the magnetic force action on that coin because of the configuration that you have in the system.
Okay. Do you think the strength of the magnet will affect the experiment?
Sorry?
The strength of the magnet.
The
Strength of the magnet.
No, we didn't calculate the strength of the magnet. Actually, we took the magnetic force. You want the value of the magnetic force.
Do you think it will affect the experiment, the strength?
Of course, it would affect the motion of the coin, but as we showed by our mathematical model, actually it's a good approximation to use the dimensions of the coin to define the threshold angle for the effect of the falling motion or the reverting motion. But the magnetic force is really important for the motion of the coin, as we showed by our angular acceleration and expression, and this constant C here implies the magnetic properties of the coin.
Okay. So if the strength is weak, what happened to the oscillations?
The strength is weak.
Yes.
Weak. Could you get some?
If the strength of the magnet is low.
Okay. It would happen, but the force will be weaker. We could have different periods of oscillations and so on.
Are there other stable? Are there other? Yes. Aside from the standing vertical, are there other stable equilibrium aside from the standing vertical or when? Is there any other stable? Are there other stable equilibrium apart from when it is standing vertically or lying down? Standing vertically or on the?
Yes, there is a stable equilibrium, as I showed in my first slide, I think. You have two conditions for the stable equilibrium, one in which the coin is placed over its thickness, and the other one in which it is like laid down over the magnet. And then we have the unstable equilibrium when the threshold angle for the falling of the reverted motion is defined.
No, I'm saying are those first two the only stable equilibrium in the experiment?
No, we haven't tested because it wasn't the objective of the problem. It's just I just mentioned it to make some introduction to the problem.
What parameters of the magnet are relevant, like the mass, moment of inertia, and so on?
Of course, the moment of inertia is important, and we did use parallel axis theorem to get the moment of inertia. And then we apply to our mathematical model for the angular acceleration. And as the angular acceleration is the integration of it in function of the time, is the angular velocity, we could get d omega over d theta 1 times d theta 1 dt is d omega d theta 1 on omega, and then integrating both sides of the equation, we have the angular velocity, and so we can get that the moment of inertia is implied in the angular velocity of the coin. So that's really important.
My point is that is this only the only relevant parameter of the magnet?
No, of course it is not, because actually it is evaluating the motion and not like the parameters of the magnet, like magnetization or something.
How relevant are the magnetic properties on the coin? How relevant are they?
As I talked before, the magnetization is really important because you have magnetic momentum, and this is the main cause of the phenomenon. This is what causes the coin to oscillate or to fall down or to get its motion, whatever it is.
So which material do you use for your coin? What type of coin do you use?
It is actually, they are actually coins made of steel. We got it. It was made of steel. It is not the real coins. It is coins that we made just for the experiments. They are uniform. They are cylinders of steel with different diameters and with different thickness. So we can get the radio between this thickness and over this diameter to get our experimental data to compare with our theoretical model.
You're saying that you only use steel material?
Yeah, because we needed ferromagnetic materials.
And also, what parameters determine the threshold angle for this experiment?
What? Sorry?
What parameters determine the threshold angle in this experiment?
I'll show you again. This is a threshold angle experiment.
I'm sorry, can you make the full screen? It is,
Oh, of course.
It can cover the scene. Thank you.
You have the experimental points of the threshold angle in function of the radio R2 over R1, that is the thickness over the diameter. And then we have the angles in degrees in which you have the coin is starting to fall down over the magnet. And it complies with our theoretical model within the uncertainties of our experiment.
And when exactly and under what conditions would you say that the coin is under unstable equilibrium?
Unstable equilibrium. As I talked in my experimental setup, we were inclined in 1 by 1 degree, each one of the coins with a non-magnetic material, of course, getting with a protector the angles in which the coin is inclined. And we made 10 times for each point, and I actually have the experimental table if you want to see all the variations here. This is a table I animated Pentac. You see the average of this data, and we have the percentage error in relation to our theoretical model. This is the angles for each one of the coins that passed.
Do you think do you think there are energy losses in this experiment?
As I talked before, also, it is. We do believe that it's due to the eddy currents. That's sorry. Due to the eddy currents, you have a variation of the magnetic flux while the coin is oscillating because you're changing the angle in which it is inclined in relation to the magnet. And then you have the induction of electrical currents. And this induction of electrical currents generate magnetic flux in the opposite direction, which generates some sort of dissipative force. And also in the fourth experiment we see that the coin with the largest area had the highest damping. So it's an evidence that the eddy currents are the source of dissipative force, because the largest the area, the largest the magnetic flux variation.
Finally, what will you conclude about this problem?
I can show my conclusions again. You have the threshold angle that is dependent on the dimensions of the coin, as we showed by the second and the third experiment, because we tried to evidence that our mathematical model works, and also that the magnetic properties and the eddy currents are important for the oscillations of the coin, which was one of the objectives of the problem.
So, do you think you answered the question? The problem?
Yes, of course.
Thank you.
Is the oscillation harmonical?
No, it is not, because actually we were expecting to get a graphic that resembled a harmonic under the harmonic oscillation, but with the period varying. So it's not a harmonic oscillation. I'd like to emphasize that.
And
Because
what is the reason that this oscillation is not harmonical?
Because the magnetic force doesn't vary linearly with the distance of the coin in relation to the magnet. It's not linear, the relation is not linear.
And another question, are the energy losses only due to the eddy currents?
As the friction forces were static, because you have the static contactor points while the coin is oscillating.
But
We
the
can
contact point changes when the coin oscillates on the one side. There is one.
I can show by my video that the contact points are actually in
There are two contact
in
points.
the extremes of the magnet. So we do believe that
Are there any energy losses when changing the contact points?
no, because the contact points are static.
I don't think so. But I wanted to ask another thing. If the coin falls down on the magnet, is this a free fall or
Of course not.
And have you studied this? The falling down of the coin on the magnet?
Yeah. Our angular acceleration here is the same angular acceleration is applicable when the coin is falling down onto the magnet, and it's definitely dependent on the magnetic properties and in the angle in which it is inclined.
Can you go please to slide 11? You're on slide 11. What is this constant C?
Oh, it's the constant that we defined it.
And how have you defined it? Yes.
Here, it's just an approximation. We didn't know the value of it. We couldn't test the value of it. So we put an arbitrary constant C that implies the magnetic properties of the coin. And then we wanted to apply this to get our mathematical model. Actually, was cancelled.
Another question, is the threshold angle only depending on the dimensions of the coin?
As I showed you in experimental data, of course it is an approximation, but it actually works.
It is not also depending on the strength of the magnetic field produced by the magnet?
Yeah, but it's an approximation that actually works with our experimental data, because the magnetic momentum is approximated to those point magnetic charts. We did an approximation, tested, and within our uncertainties that actually works in reality.
Okay, and the same question to the one. Is the threshold angle only depending on the dimensions of the coin?
Yes.
First, I'd like to thank the reviewer for the presentation, and I'd like to talk about some points that she mentioned. She said that I considered the harmonic oscillation, but actually I said, even in a great remark here, that it should resemble the behavior of it, but we weren't expecting actually to get a harmonic oscillation. We were expecting to get periods that vary with time because of the non-linearity of the force in function of the distance. When I said that the angles were dependent only on the dimensions, I clearly said that it was just an approximation for that we made our mathematical model because because it is hard to predict the magnetization on the coin from ferromagnetic materials. And our model actually works when you try to, within a certain deviation, when we try to compare with our mathematical data, experimental data. She said that I didn't evaluate the fall motion. Actually, these equations here are applicable to the fall motion, of course, and we see the behavior of it because in these first angles here, it is under the threshold angle, so it is falling, and the behavior is that, and then you have the behavior of the falling motion. And about the diamagnetic and paramagnetic materials, I haven't tested because actually real coins are made of ferromagnetic materials, so we made delimitations for the problem. And the comparison of the oscillations with our theoretical model. Actually, I made some qualitative with the behavior of this graphic. I've made some qualitative comparison with what we were expecting to happen. And that's all. Thank you for your attention.